we're very, very happy that Lucia is here today. She's a presidential postdoctoral fellow at, in the Department of Civil and Environmental Engineering at the Princeton University right now. She has a PhD and MS in mechanical engineering from Boston University and a BS in mathematics with minor in Hispanic studies from Davidson College. And her research is about fundamental finding nonlinear mechanics and instability of slender structures. Okay, take it away.
Thank you, Ellen, for the intro, and thank you all for being here. I appreciate it. I'm going to talk about my work on shape-shifting from fundamental mechanics to cities. So, let's see. All right, does this work now? Okay, so in this animation, you're seeing the transition from countries where the majority of the population live in rural areas, shown in red, to where the majority live in urban areas, shown in blue. And so this urbanization trend is clear, and it's going to project into the future. And in fact, by the year 2050, it's expected that 68% of the world's population will live in cities. And as we continue to develop cities, we're not only changing skylines, as you're seeing in Shanghai between 1987 and 2013, but we're also changing the microclimate. And so this increasing urbanization is happening at the same time that we're feeling a lot of the effects of climate change. And so temperatures are rising globally, but this effect is felt even more strongly in cities. And this is the urban heat island effect, which is due to things like surface properties and the morphology of cities, which can trap heat and impede ventilation. And so we're seeing kind of a rise of contaminants in cities now with increasing wildfires, as you're all well aware. And cities are, in general, not very well equipped to handle the impacts of rising extreme weather conditions. And so this is because currently our cities are largely comprised of static structures that can't self-regulate. And so we need a lot of interventions for things like cooling and heating. And in the United States, buildings account for 39% of total energy consumption. So if we want to think about designing new city spaces and adapting old ones so that they're more resilient to the effects of climate change and urbanization, it would be much better if we could design them to be more self-regulating and lifelike. And so one great way to do this is to quite literally reintroduce life back into the city in the form of vegetation. And so green roofs and walls are a great way to reduce temperatures and improve air quality. However, due to either the integrity of older buildings or the local climate, a lot of spaces in cities are not amenable to this type of vegetative cover. And so this is where engineered solutions come in, and in particular, adaptive architecture designs. So this is a famous adaptive shading facade at the Arab World Institute in Paris. Each of these individual apertures of different sizes can open and close in response to a sunlight stimulus. And it's really effective at reducing the need for cooling intervention in this building. But as I think you can see here, the mechanism is rigid body motions of slender structures that require a lot of electronic actuation, and there are a lot of moving parts here. And this facade was famously frozen in place and then under repair for years. So if we want to think about kind of building on and maybe improving upon these types of designs, my suggestion would be that we kind of step away from these rigid body motions that require complicated input to move, and instead turn toward shape-shifting structures that are relatively happy to deform in large nonlinear ways. And so what do I mean by that? Well, when a structure is forced to deform, it will do so in a way that minimizes its total potential energy V, which for elastic bodies consists of the elastic strain energy U and the potential P from external loads. For slender structures like rods, plates, and shells, for which the thickness H is much smaller than at least one of the other dimensions, then in general, we can write the elastic strain energy as a sum of two terms. One that penalizes deformations due to stretching or compression, and one that penalizes bending deformations. Now the stretching energy scales with the thickness H, whereas the bending energy scales with the thickness cubed. So you can imagine here, if this thickness H gets smaller and smaller, it becomes much cheaper energetically to bend than it is to stretch. And so the result is that slender structures will undergo wildly nonlinear deformations in order to avoid stretching whenever possible. And sometimes these nonlinear deformations can come on suddenly or even unexpectedly, and this is known as an instability. There are two main types of elastic instabilities. The first is buckling, and the canonical example is of a column under a compressive load. So if I start to increase the load on this column, it will reach a critical point where the load path becomes unstable and the structure will deflect in one direction or the other. And this is a bifurcation instability. And so an example is of railroad tracks, which can swell due to thermal expansion from the sun. This causes a compressive stress to develop, and buckling can occur in kind of catastrophic ways. Snapping is the other main type of elastic instability. And the example here is of a truss, which is loaded at its center. And so I increase the load, it reaches this critical point where the load path is unstable. And the nearest stable point on this load path is kind of quite far away in terms of the deflection W. So the structure will rapidly snap through to its inverted state. And an example here is of an umbrella, which can snap through in the wind. She'll make it snap back into place, and then this guy comes over and reinverts it for some unknown reason here. Now, these are kind of quasi 1D examples of instabilities. But in 2D, where material constraints start to play a role, instabilities, and in particular buckling instabilities and post-buckling deformations, can look a lot of different ways. So, for example, differential growth leads to an excess length at the edges of this flower that causes compressive stresses to develop, and this wavy pattern is the result of a buckling instability. Wrinkling is also a buckling instability that emerges due to compression while being confined to a soft substrate. And many of the morphologies in Earth's crust can also initiate from buckling instabilities. And so generally speaking, these deformations and instabilities are highly sensitive to geometry, material properties, and boundary conditions. And so the point here is that if we as engineers can understand and control these types of instabilities, then we probably have access to a wide range of morphologies for our shape-shifting engineering designs. And so people have been doing this for the past couple decades, kind of across scales and for different applications, including, some of you here. So to give you some examples, at the micro scale, buckling can give functionality to stretchable electronics, and buckling of these spherical micro swimmers is what gives them their mobility. At the centimeter scale, snap-through instability of this spherical cap actuator in the cartoon here drives this soft robotic gripper. And a subfield that's kind of blossomed in recent years is that of mechanical metamaterials. And the idea is to design the geometry of the structures. Buckling instabilities will give the structure some emergent behavior, such as a negative Poisson's ratio, as you're seeing here. And also at the meter scale, local snap-through instabilities aid in the deployment of this origami shelter. And so I'm showing kind of a notable example here at the meter scale. But really, the vast majority of research on using elastic instabilities in engineering designs has been at the centimeter scale and below. This isn't to say that a lot of these deformations aren't scalable. There have been some examples in architecture of using these kind of large deformations and instabilities and designs. And so in this building facade, large bending of these panels gives the adaptive shading functionality. And in this example, each of these cylindrical shells is made of thermal bimetal. So past a given temperature threshold, they snap through, changing the lighting and thermal environment within this model room. Okay. And the mechanics community is also starting to get on board here. And in particular, in the past several years, there have been several examples demonstrating how we might be able to use kirigami for adaptive shading facades. But ultimately, this subfield is really just getting started. And in my opinion, there's a huge amount of untapped potential to connect this wealth of knowledge we have at the centimeter scale about the mechanics of shapeshifting with the need for architectural scale solutions for not only shading, but also things like regulating airflow, sound, water, you name it. Okay. And so this is kind of the overarching goal of my research, that is to understand and apply the mechanics of shapeshifting, which is to say, compelling structures to adapt a different configuration on demand or in response to a stimulus, to develop adaptive designs for flexible, sustainable, and resilient urban spaces. And so my work in this area has spanned from quite fundamental on this really, can we understand these fundamental deformations and instabilities and shapeshifting, to more applied toward these architectural applications. And so I'm going to kind of bounce between those ingredients in this talk. I'm going to talk first about an application which is using kirigami for ventilation. Then I'll talk about one of these fundamental topics, which is how do shell structures buckle in response to confinement. Then I'll talk about confined plates and how we can use them at the intersection of art and architecture. And then I'll go forward to talk about future work, which is really more in this direction of lifelike cities based on shapeshifting and incorporating other surrounding physics. Okay, so I'll start here and talk about using kirigami for ventilation. So as I said in the introduction, cities, because of their morphology, are often prone to poor ventilation patterns, and this is true especially in the urban canyon, so the space between rows of buildings. And furthermore, kind of retrofitting structures that pop up within our urban canyons, like these streeteries or parklets or canopies over the urban canyon, which are common in southern Spain, for example, are, they're there to serve a purpose to provide shelter and or shade, but they can also really exacerbate these ventilation problems. So our goal with this work was to kind of redesign these types of retrofitting structures so that they will not only be able to provide shade, but also improve ventilation of a space beyond what it would be in the absence of shade. And so the approach we take is based on kirigami, or cutting paper. So I've added this pattern of linear parallel cuts to this sheet, and then when I stretch it uniaxially, those unit cells that I've created buckle out of plane and rotate. And our hope is that those angled shoots will be able to steer wind into spaces with stagnant air to ventilate them. Now, from the perspective of adaptive architecture, kirigami has a lot of potential benefits. It's very easy to make and customize, and it's waste-free, it's flat packing, and it can be actuated with this uniaxial stretching, so a single degree of freedom actuation. The mechanics of kirigami have been really very well studied, and so I really have this library of literature that I can turn to that tells me how changing the cut pattern will change the resulting deformations and mechanical behavior of these structures. So as a result, if we're thinking about using it for ventilation, my job is really to focus on the fluid mechanics side of things, where a lot less is known. And the interaction between kirigami and a fluid is quite complicated and complex. But as I said, we think that the most important feature for ventilation is going to be these angled chutes here. So I can approximate this as this kind of quasi 2D approximation as these angled slats or louvers. And so what we did in this study is basically take this simple geometry, use it to kind of quickly vary the geometry and find design guidelines that I can then use to inform my kirigami designs. And so that's what I'll talk about. I'll talk about our results with these louver approximation kind of briefly, and then I'll bring it back to kirigami and see how we did with these designs for ventilation. So I study this with experiments primarily, or that's not true, with experiments and simulations. But we first asked this kind of fundamental question of how do these angled features interact with oncoming wind to ventilate a standalone enclosed space, which is this shallow box here that you're seeing. I perform experiments in a wind tunnel. So there's an oncoming wind in the range of 3.5 to 25 meters per second. That corresponds to a Reynolds number on the order of 10 to the 4th or 10 to the 5th. And as maybe a reminder, this Reynolds number is the dimensionless number that I need to keep more or less constant so that the things I learn about this kind of scaled down model will apply to realistic urban flows. So this corresponds well to what we would expect for a typical streetery or parklet, and it's about 1 order of magnitude below what we would see in a typical urban canyon. I perform particle image velocimetry or PIV measurements on the system, which means that I'm seeding the flow with aerosolized oil particles, illuminating those with a laser, and then taking high-speed images of this. So that gives us images of particle motion that we can reconstruct a velocity field from. At each camera position, I need to take 2,000 pairs of images at a rate of 25 hertz, so it's 80 seconds of data. And to construct the full plane of this box, I'm taking data at 4 different camera positions. And so I also did computational fluid dynamics or large eddy simulations on this system. Large eddy simulations strike a good balance between resolving turbulence and computational efficiency. I used ANSYS Fluent with kind of standard LES solver settings. And so the domain mimics that of the wind tunnel. And a typical simulation can look something like this. And if you see time average data from simulations, that's over a course of 20 seconds, starting at t equals 20 seconds. So after verifying that our experiments and simulations agree, which I'll show you later that they do, I can then use the simulations to vary the geometry widely and relatively quickly. So our kind of reference case, as I've sort of alluded to here, is this open box with no, say, shading structures. And so what happens when flow approaches from the left is that this shear layer develops that drives air to enter toward the back of the box, recirculate quite a bit, and then exit near the front of the box. In contrast, if I have these 3 kind of large protruding louvers, the upstream louver is able to intercept that shear layer, drawing air into the box, creating these large sweeping flow structures that can then exit downstream and re-entrain with the gold flow. So from the perspective of ventilation efficiency, this is already probably a good thing. We're no longer just recirculating these particles. And if I vary the geometry more widely, we can see we observe these kind of similar flow patterns over here where we have these kind of large protruding features. The effect dies out until when I have a lot of small louvers, we more or less recover the flow patterns that we see in the open box. So I can quantify what this means for ventilation in terms of the air exchange rate, and what this expression is calculating is essentially how many box volumes of air do I empty per second. And so can come to our reference case and compute that quantity and then compare it to the rest of our data. And so for the geometries that I studied, this is the curve we obtain. So we can identify then this geometric regime wherein the addition of these angled features or louvers increases the air exchange rate above that for the open box, which is what we wanted to achieve. And we can use that to inform our kirigami design. And this corresponds, this geometric region corresponds to where we have these larger protruding features that are creating these large sweeping flow structures. So I can design my kirigami accordingly. I have these large unit cells, a low number of unit cells, and I'll do experiments in just the same way. Except since the kirigami isn't homogeneous into the plane, I'm going to take data at two different vertical planes now. So this vertical quarter plane and a vertical midplane. For simulations, I need kind of a few steps now. So first I do a finite element buckling analysis in Abacus. I export the deformed geometry, and after an intermediate remeshing step, I import that back into ANSYS Fluent, and then I do the CFD or LES simulations in the same way. And so I'm treating the kirigami as rigid here now. So this is a one-way fluid structure interaction in the simulation. And when I do that, then we can start to take a look at how kirigami interacts with the flows in different planes. And then we can also look at this time average data here. So this is data from experiments in the vertical quarter plane. On the top is the time average streamwise velocity, and on the bottom is the mean vertical velocity. We can see that that compares well to simulations. And the same is true in this vertical midplane. I can also then compare this time average data to our kind of guiding case, which was these kind of three large protruding louvers. And we can see that we're creating kind of similarly large flow structures. So then we can come back and quantify this. This is the same data that you've seen for the air exchange rate for louvers. I'm just normalizing the y-axis by essentially the inflow velocity here. And then we can add our kirigami data point, and we see, okay, this is, first and foremost, we increase the air exchange rate above that for the open box, which was the goal. And we're also seeing that this data point falls really quite in line with the data for this quite simplified geometry, telling us that this pretty significant geometric simplification was probably a pretty good informative one for this type of design. And there's certainly room for optimization here. One thing that might be kind of unsatisfying so far is that it looks like this most upstream unit cell is really doing most of the work in guiding ventilation, right? And in this paper, we kind of quantified that in two different ways, and this is the case. So if those downstream units aren't really doing much to help ventilation, we might be able to put them to better use. And so everything I've showed you so far has wind approaching from one direction with respect to positively oriented louvers or kirigami units. If the wind were to come from the other direction, or equivalently, if I orient these units in the opposite way, we see really a reduction in this air exchange rate. It becomes comparable to the open box, and it's significantly below that initial configuration. However, if I orient these in non-homogeneous ways, we can raise the air exchange rate again, and even to slightly above that for the open box. And I'll point out that these top two configurations are the reverse of one another, so wind could approach from either direction and we would still be in a pretty good ventilation regime here. With kirigami, I can change the cut pattern just slightly so that these unit cells are bistable. And so that means in the same structure, I could have coexisting unit cells oriented in different directions, and we could even switch between them in situ. And this is documented in the literature, so all I really need to do is take my geometric constraints related to ventilation, match that up with geometric constraints for bistability, and this is our design space here. And similarly, it might not be shocking to learn that changing the angle of orientation changes the air exchange rate. So for example, if you had uncomfortably high wind speeds, you could close them off to reduce that. And with kirigami, this is certainly tunable in situ with this uniaxial stretching. This video plays, yeah. And again, this is documented in the literature, how the axial strain, so the stretching compares to the feature angle. So these kind of actuation ideas are things that I'm thinking about going forward. How can we achieve these things in real structures? And we're also thinking about studying more realistic urban archetypes, such as these urban canyons. And so in this first paper here, it was kind of a proof of concept that kirigami can work for ventilation and validating our methods. And going forward, these are the kind of questions that I'm thinking about with this work. So I'm going to shift gears here. But before I do, I want to really reemphasize that in this first project, I really focused on the fluid mechanics side of things because the mechanics of shape-shifting of kirigami were very well documented and well studied in the literature. But for other kinds of designs that we might want to do with shape-shifting structures, this is not the case, and we need to do a little work to understand the fundamentals. And so I'm going to shift gears to talk about one such system. So shell structures are abundant in nature and oftentimes are confined in some way by their environment. And I think that confinement of shell structures will be a useful, I'm having a loading thing here. I think confined shell structures will be useful for designing kind of robust adaptive facades. And I'm going to come back to this when I talk about future work. But at this point, the confinement response of shell structures, which are curved, is really not very well understood in the literature, with the exception of kind of specific cases like the indentation response of positively curved shells. So we wanted to take this kind of broad sweeping approach and ask how shell structures that vary in their geometries respond to confinement. And to do this, I use primarily experiments, and I used a technique called residual swelling. So we take these two polymers, which have different hardness ratings and different concentrations of free chains. I cure them one by one in contact with one another. And when I do so, there's this concentration gradient of free chains. So in a diffusive-like process, those excess free chains will migrate from the pink polymer into the green one. That causes a loss of mass to the pink polymer and an increase of mass to the green one. This leads to a geometric incompatibility, which causes these structures to develop a natural curvature. So I can kind of arrange the different polymers and molds in different ways to create a variety of shells. And so I studied 4 types of shell geometries. The first is saddles, rolled sheets, cylinders, and spherical segments. And so in this initial unconfined state, each of these structures has 2 lobes. And what I'm going to do is add confinement. So I clamp the top 2 shells in their central region between 2 acrylic plates. And on the bottom, I'm clamping them at their base. And when I do that, we see buckling into an additional higher mode number. I'll just define a few geometric parameters here. So the overall radius of the shell is big R, and the free length, so the distance from the clamp to the edge of the shell, is little r here, which for saddles and sheets is that distance that you're seeing, and for cylinders and spheres is essentially the height. Okay. Now, if I progressively decrease this free length r, what we see is buckling into higher and higher mode numbers. And so I have these shells that vary widely in their average Gaussian and mean curvatures. The geometries are very different, but we're seeing this global behavior among all of them that's really quite similar. So we wanted to understand what's underlying that. Can we reduce it to its simple physics and to geometry? So to do that, we can come back to this elastic energy, which, as I said, all of these structures are trying to minimize. And we can say that one main contribution is definitely going to be bending in the circumferential direction. I can approximate the curvature in the circumferential direction as shown. And then if I just kind of unwrap the edge of this shell, this is what it looks like. To compute a bending strain, I need to compare that to its reference state, which looks like this. And then I can plug this in to the elastic energy using some geometric identities, write an expression for the elastic energy bending in the circumferential direction. And so the takeaway here is that from the perspective of the circumferential direction bending energy, it wants to preserve these long wavelengths, which means it wants a low mode number. Something's clearly opposing that because we're seeing higher mode numbers. And what we think that is bending in the radial direction. So I can do a similar thing here. It's loading again, but I'll write an expression for the curvature in the radial direction and compare that to the reference state and plug this into a radial direction bending energy term. The takeaway here is that from the perspective of the radial direction bending energy, the structure wants to preserve this ratio. So if this free length r gets smaller, it wants a lower amplitude, which means it wants a higher mode number. So we think these are the 2 competing ingredients here. And so I can carry out an energy balance, which means I'm going to equate these terms, which is equivalent to minimizing this elastic energy. And when I do, I come up with a scaling for how the mode number should depend on this geometric parameter, which is the ratio of the overall size of the shell to the free length. And I'll call this geometric parameter L. Before I plot this against our data, I'll kind of recover some prefactors here based on the minimum value of L. And for saddles and rolled sheets, that prefactor is different than it is for cylinders and spheres. So I'm going to plot these things differently on the next slide. And what we see is that this single geometric parameter seems like it's pretty well able to capture this global behavior across this wide range of shell geometries. And I'll also point out, these are linear axes, not log logs, so we're seeing a pretty good linear trend here. Okay. And furthermore, there doesn't appear to be a big dependence on the thickness on setting the mode number over the range of shells we studied, which tells us that we were probably okay in neglecting the stretching energy in this energy balance. So we have this understanding of how geometry governs the response to in-plane confinement. We then went on to ask what happens if we vary the transverse confinement. And so when I release some of this transverse confinement, the buckling mode decreases progressively, and vice versa. If I increase the confinement, the buckling mode increases. So in this paper, we studied the force response, and we also kind of modified this scaling to account for this transverse confinement as well in a kind of quasi-empirical way. But so we come away with this good understanding of how geometry governs the response to in-plane and transverse confinement for a wide range of shells. And by reducing this to geometry, it means that the things we learn can apply to different materials and stimuli, and thus can be used for a range of applications. And so I'm going to come back when I talk about my future work and talk about one that I'd like to go forward and study. Before I do, I'll talk about another kind of confinement problem on the fundamental side. And then if you bear with me, I'll talk about how we're using it in kind of at the intersection between art and architecture. Okay. So compared to the confinement response of shells, which are curved, the confinement response of thin sheets has been really well studied. And we have this kind of intricate understanding of how intrinsically flat thin sheets respond to confinement. And so under relatively weak confinement, the energetically preferable deformation response is to wrinkle. And this is a way to kind of distribute all the stretching and bending across the whole structure. However, if under kind of stronger confinement, it becomes energetically preferable to stretch and bend a lot, but only in these small sacrificial regions, which are stretching ridges and vertices. So we can take a close look at the structure of one of these vertices by taking a piece of paper, placing it on top of a ring or your coffee cup and indenting it at its center. And so this buckled structure that forms is the developable cone or D-cone. So all of these radial directors remain unbent or developable to a flat sheet, which means that no stretching has occurred in the bulk of the structure. And instead, all of this energetically costly stretching has been focused to this core region. The D-cone has been really well studied, especially from a theoretical perspective, and it's understood in particular that the size of this kind of dislocated buckled region is said to be independent of materials and geometry in kind of an idealized system. But so we thought there's probably a lot going on kind of away from these idealized limits. And we wanted to understand really what happens in the middle or in the kind of question mark stage. And in particular, we want to reduce this again to the role of geometry for the same reasons as in the past study. So to do this, we perturb this ideal D-cone structure by once again clamping its central region. So where it wants to focus all of its stretching and bending, it can no longer do so. And instead it takes on this kind of circumferential buckling pattern. To study this systematically, I'll define three geometric parameters: the radius of the clamp, RC, the radius of the ring, RR, and the radius of the plate, RP. And I study this with experiments using an Instron machine. So that means I can impose displacement and measure force. And so initially this clamped plate assembly rests underneath this ring here. I'm going to pull it upward quasi-statically a distance d, and then we can watch from below with this upward facing camera as it deforms. And I'll just define a dimensionless packing parameter, which is d over this length here, RR minus RC. So when I do this, we can see what happens, and we observed a kind of rich series of deformation sequences that was, I don't know, a little surprising to us in some ways. So in this video, I'm pulling from behind the screen through a ring, this clamp sheet. And what we see is that at small epsilon, at early deformation stages, we see this kind of subtle low amplitude wrinkling in just the outer region of the sheet. So this is a stress diffuse deformation. And then we see this sudden transition to stress focusing when truncated cones form sequentially. I'll let this play again, and I'll also show you some molecular dynamic simulations from my collaborator, which are able to reproduce these this sequence of deformations. And the color bar here is the bending energy density. So you can start to see this kind of focusing all the energy into these regions near the clamp, right? So because these are performed on an instron, I can also take a look at the force response here. And when each new cone forms, there's a sharp drop in the force displacement curve. The images you're seeing popping up are 3D scans, so they're from experiments. And in this paper, we study the force response kind of in detail, but here I'm just going to focus on the geometry side of things, and in particular on the size of this dislocated region, which, as I said, for the D cone is supposedly independent of geometry and materials. In our system, it looks like it's really sensitive to geometry. So we wanted to understand, of course, why and how do our geometric parameters that we're controlling relate to this geometric outcome. So if I keep everything constant here, except for I'll increase the size of this central constraint, we see buckling into higher mode numbers, and at the same time, the size of this angular cone decreases. So I just write this kind of empirical scaling here. We observe over kind of a wide enough range of our data that we see kind of the opposite dependence on the radius of the ring, RR. And so we have this empirical scaling. I can check it against all of our data. And we see that this does okay. When you see the plot, you'll agree with me. Let's see. It's loading, yeah. Okay. So over here in this range where the radius of the clamp is comparable to the radius of the ring, there's good agreement with this scaling. But as we get closer to this D cone limit where the clamp is really small, there's really quite a lot of scatter. And in fact, what we see is this kind of diverging trend where in this D cone limit where the clamp is small, the effect of the clamp is kind of forgotten by the structure, and instead the overall radius of the sheet becomes more important. We also see this inversion in the role of the ring radius, RR. I can summarize this in kind of a piecewise empirical function, and I'll just point out that this horizontal line is from the literature for the D cone that shouldn't depend on geometry. We're seeing that in our kind of realistic sheets and also in data from the literature, there does appear to be a geometric dependence even in that limit. So we come away with this understanding, if empirical, about how geometry dictates these buckling patterns. We also understand the forces quite well. So we went on and I was thinking also these are kind of lovely buckled shapes and kind of flowery and beautiful. And then that got me to think about other kinds of flowery or plant structures that can open and close in these similar ways in response to, for example, sunlight or human interaction. Let this play. So then we started thinking, I came to Princeton and I'm working here with architects and roboticists, and we started thinking, can we kind of make a bunch of these structures and put them together and use them for light manipulation? Can we play with their response to light, with one another, and with humans? And so this is what we're working toward. My collaborator, who's a roboticist, put together this prototypical unit, and we have an Arduino in here that can detect motion and respond. So this is kind of an early prototype here. The geometry are squares now so that they tessellate the plane and kind of block light if they're all the way open. And we can now use that to play with human interaction and let gestures guide these kinds of deformations. And so we're building this up and we're putting together an exhibition, which will be on campus soon in April, which is this interactive art/architecture exhibition where people will be able to interact with these kind of buckling structures. Yeah, that's something I'm really looking forward to. So I'm going to talk about future work, but before I do, I'm going to give you some very big picture takeaways about what I've talked about so far. So lifelike designs could make cities more resilient to the effects of climate change and urbanization. Understanding the mechanics of shapeshifting and the other relevant physics like airflow and so on can enable the design of environmentally regulating adaptive structures. And experiments, simulations, and simplified models can reveal generalizable and geometry-based design guidelines. I want to thank my collaborators on this work that I've talked about here so far and my funding sources as well. And with that, I'll go on to talk about some ideas I have for future work, which are really in this direction of adaptive architecture and lifelike cities. And so the overarching goal of my future research program will be to design adaptive structures for sustainable engineering. And in particular, our goal for, I think, the first 5 to 10 years would be to develop technologies aimed at rendering cities more lifelike and resilient so that they're capable of regulating things like airflow, light, temperature, water, sound, and energy. So I'll kind of dig into a little bit to three project areas that I'm interested in working on. The first is tailoring urban airflow with mechanical metamaterials, not just to improve ventilation, as I've talked about so far, but also for comfort on the other side of things when you want to reduce wind speeds. Second is to develop robust, adaptive, and cooling building skin elements. And the third is urban soundscape management based on curved creased origami. So I'll start here. And I would say, first of all, in the work I showed with using kirigami for ventilation, I think there's still really a lot of optimization to be done. I think we can play with non-homogeneous cut patterns, as well as upscaling and thinking about multi-physics. So can we also play with sunlight and redirecting light, and also, solar energy harvesting, things like that. So I'm interested in continuing work on that project. I think we can take it a lot further. But on the other side of things, I think we've all been in spaces and cities where you're like in a wind tunnel, there's this channeling flow, and it becomes really uncomfortable or even dangerous. And so there are certainly other spaces in cities where we want to kind of tame these kind of flows. Trees and specific kinds of trees are great at doing this, but in spaces where we can't just plant these kind of trees, engineered solutions often look a little more like this. So these kind of big material intensive, quite permanent structures. So if we want to make this kind of more adaptive and more tree-like, I think an approach that would be nice is kind of redesigning these types of structures with mechanical metamaterials broadly defined. So kirigami, origami, and textiles, I think would be interesting to explore here. So I know some of you here are probably working on that and or on using textiles in general. So I think that would be a fun collaboration area. And the goal here is to design these kind of mechanical metamaterials so that when they're loaded by wind, the shape and porosity they take on is able to tame these wind loads and to redirect wind in kind of nice ways for us. And we want to do this up to the meter scale. The second area that I'm interested in working on is about building skin elements. And so if I come back to this idea of how can we improve on these types of designs and make them require less kind of complicated input to move. Material science advances have gotten us kind of a lot of the way. So really the goal is to achieve large, reversible, and fast deformations in these types of materials like thermobimetals, hygromorphic wood, shape memory alloys and polymers, and biocomposites. This one responds to moisture. I think they get us a lot of the way there. We can have these large and reversible deformations, but the problem really is that on architectural scale thicknesses, the deformations we would need are taking on the order of hours for a lot of these materials. So my kind of dual approach to skirt some of these materials challenges using mechanics would be first to use these types of materials, but sparingly and in combination with passive elastic materials. And second, to use geometric confinement, which we've seen is kind of very controllable through geometry and can lead to fast reversible shape change. So I think that using these kind of techniques, we can play with, first of all, developing prototypical building skin elements that can regulate shading at the centimeter and then meter scale. A fun extension of this, I think, would be to play with retroreflective materials so that we're not only impacting inside this building, but also the surrounding environment. And also thinking about solar energy harvesting, so embedding PV panels, things like that. If we can do this, I think we could take it a step further and think about hydroactive morphing. So responding to water, to rainwater or moisture in the environment. So these panels could morph to provide things like shelter or redirect water for storage or irrigation. And I am also really excited about the idea of kind of multi-scale morphing. So these are the large scale morphing ideas, but on kind of the micro scale of these structures, we could also think about capturing water for evaporative cooling. So in this sense, I think there's a lot of room to play also with materials. So we could think about porous materials, not so much kitchen sponges, but porous mechanical metamaterials, kirigami, textiles, granular materials, and biomaterials or bio-inspired materials. And so these are the feathers of the sand grouse bird, and they use elastocapillarity to capture water droplets and carry them to their young. And so I think there's a lot of room to play kind of on the structural and material side of things here. And so that's another area that I think collaborating with folks in Atlas would be really fun. And then the third area here is about urban soundscape management. So the World Health Organization recognizes environmental noise as one of the top threats to human health, and it's also certainly a threat to biodiversity and ecology in cities. the kind of sound barriers that we see nowadays are, again, these really large and very permanent structures, which means that for time varying or temporary noise sources, we don't really have many solutions right now. And so the solution I propose is based on curved crease origami. So with traditional origami with straight creases, folding doesn't cause panels to bend, the panels remain unbent. When creases are curved, folding leads to panel bending. And we've shown in these works here that this is really quite controllable through the crease curvature and through loading. And so the idea then is to play with this panel curvature and the interaction with sound waves. So the first idea or the first task here, I guess, would be, I think, probably at centimeter scale in experiments, study how we can shape sound waves based on panel curvature for different origami folds. And then in kind of a parallel thrust, can we make these curved crease origami structures at the meter scale so that they're stable against wind and gravity loads? And so those are, yeah, kind of two parallel thrusts on this work as a first step. And then I would like to take this a step further and think about multiple of these, say, acoustic lens elements based on curved crease origami. So we could have several standalone structures for kind of a finer control of the soundscape. And then we could think about tessellating these things so that you can impact sound through local deformation, so through each individual unit, or through global deformations of the entire structure. So kind of an acoustic metamaterial type design. And again, here, I think there are, folks that are working on sound and music, and we could probably come up with some fun, unexpected collaborations. And on this last topic, I think this would be a great place to collaborate with people who are working on sensing and robotics in this institute. And I would just say, as kind of a general statement, I think this kind of human architecture interaction compares really well to human robot or human computer interaction. So I think there are also a lot of fun avenues we can go with that. And the last thing I'll talk about is that I really prioritize and integrate this idea of inviting science into my research. And so a bunch of my research is inspired by art forms. And I think that especially these kind of meter scale, in your face interactive demonstrators are a great way to engage people who might not otherwise be interested in engineering. And so I proposed several of these kind of meter scale interactive demonstrators for my future research. And I'm excited to get working on these kinds of things. So with that, I'm going to leave you with a big picture summary of my research spanning from these fundamental mechanics of shapeshifting to using shapeshifting for things like shaping wind and light. And then in the future, I think there's really a lot more we can do to play with these surrounding physics and impact urban designs. And I'm happy to take any questions. Thanks for your time.
I have a question. Sorry. So as far as the first fascinating work, really cool.
Thank you.
How much of your work extends into the sort of like capturability and kind of reusability of these types of materials, as far as how they extend from sort of like their implementation and then sort of repurposing or sort of recycling?
That's a really good question. I think a lot. So yeah, thinking about like sustainable materials is certainly at the forefront, as is thinking about kind of frugal design as much as we can. So as an example, I think for like the kirigami shading and ventilation, I could imagine just like giving someone a template, say like cut up your bed sheet and do this and use it. I think so it's factors into the idea behind this, I think, sound project in the future. Very much. The idea would be that these are reconfigurable. You can move them around. It's like a temporary, I don't know, meeting pod within an office, or it's bigger and it's outside. And so that's definitely a consideration for that project in particular. And I do think, in both that and then the airflow, kind of taming wind speeds, another idea is like, these are really ways to reduce the amount of materials we're using, like flexibility leads to robustness. And so I do think it's kind of a reduction standpoint, and yeah, for reusability, I would like to think that a lot of these things could be reconfigurable and you could move them around as you like. Yes.
Amazing talk.
Thank you.
I was wondering about the sort of adaptability for some of these materials like the kirigami, others. When you think about the future of implementing these on large scale in cities, do you lean towards sort of software manipulability for the materials, or the materials themselves sort of reacting?
That's a very good question. I think ideally for me, they can be kind of passively responding. But there are challenges to, like, I think probably some hybrid approach is the most realistic and best. But like, when I say kind of using passive elastic materials in combination with these kind of smart materials that can passively respond, we would need to be clever about where we place it based on mechanics so that we can have like a minimum amount of material that's active and so things like that are kind of materials and mechanics challenges. And I do think, you know, there's certainly a place for software in these types of designs, and it would still be more efficient than our big air conditioners or things like that. So.
That's kind of a weird question, but I was wondering if you could say more about what is life like to you?
That's a good question. So what I mean by this is basically responding to the environment and moving. Like, we breathe, we sweat, we do all these things that static structures don't do. So yeah, I'm imagining kind of motion as the primary aspect that I'm going for of life like, but I think you can interpret it a lot more broadly and could probably give me some cool ideas about other like ways that we are alive. So yes.
I think this is going back to what Eli said here, also great talk, it was actually, but, have you ever experimented with like electroreactive polymers or anything like that?
No, the other, like, I've mostly, so in one project that I didn't talk about here, we were using the same like residual swelling, but also like magnetic polymers. We used like a couple different like stimulus responsive materials, but the kind of resulting theory was like stimulus agnostic. So the idea would be that it could, those kind of geometric and mechanics findings could apply to those kinds of materials. But I haven't experimented with that, and I think it would be a lot of fun.
Okay. Thank you for your talk. And then two questions. Firstly, when you were talking about the first project about airflow and ventilation, you mentioned how you ensured that small scale physical experiments would translate to how things would work at scale.
Yeah.
I was wondering if the same applies to elements of buckling and then physical deformation, especially when the material properties, when you would be using them in large scale construction, like metals and metal sheets or fiber sheets as opposed to paper. Have you looked into the ways in which findings translate?
That's an excellent question. Yeah, so the Reynolds number similarity ensures that like these flows will be similar, but you're totally right. Like the mechanics, we can't assume that in all cases. Kirigami, like it's been shown that the deformations are scalable. So I think that's partly why I kind of go to that first. I think it's a great candidate for scaling up, and we can play with this. But I think really addressing on these scales, we often don't need to deal with gravity. We certainly don't need to deal with wind loads. And so a lot of the materials, stability and actuation questions are open. And that's something we're starting to get at with this exhibition. But you know, the structures themselves are bigger. They're not bigger. So that's something I'm really thinking about going forward, is we need to be making these things at larger scales to be sure that it actually works.
Yeah, no, but the reason I also ask is, you began by talking about urbanization and the need for this to be at scale.
Yeah.
But then, even in today's world, the most compelling shape-changing architecture that I see are either skyscrapers or sports stadiums. And I think part of that is construction methods that are required for that are far too expensive and instrumented today. To what extent do you think that these ideas can fit into existing patterns of construction, and or how much do you think needs to be changed?
That's a great question as well. I think I'm thinking a lot about retrofitting designs that we can just stretch a kirigami sheet over a courtyard or the urban canyon or one of these streeteries where you don't really care much about rain and air in place or something. So I am really prioritizing those kinds of ideas where I'm not gonna build a building but I think we can add on some structures that are relatively, you know, cheap to make that can really impact these things. So that's my priority for really the reasons you said, because yeah, if we just add a lot of cost and kind of unsustainable materials, we're defeating the purpose of this research. But yeah, great question. I think some of the building skin ideas are, I think more exploratory and like proof of concept. But then there are others, like I think the large origami and kirigami stuff where we can really retrofit spaces with them.
Is that the largest scale thing that you've built based on your research at the moment?
Yeah.
The installation? Okay,
Yeah.
Cool. Cool. Thank you so much.
I'm curious, first of all, like what motivates your work? I think that there's some material stuff going on, and also some art stuff going on. And then second, I'm wondering if you could speak to when this would not be the right solution. Like, where do you feel like the limitations are?
Sure. What motivates my work is, I mean, the climate, like I studied these really my PhD was on basically this like really fundamental side of things. And I wanted and want to do more, like what can I do with this to impact anything climate related for me? And also just kind of recognizing, I really think we have this big gap where we're all doing so much at the centimeter scale here. And I think in some of these cases, yeah, there's a lot of potential to scale up. When would it not be appropriate? I think a lot of these designs are very like local microclimate dependent. If kirigami, these things I think are more appropriate for arid regions than wet ones, for example, in like a streetery, something like that. So I think there's a lot of kind of local climate dependencies. In addition, we need to think about, is this somewhere where we want more wind or we want less wind? So things like that are considerations. And then it would come back to this kind of, well, both of these kind of like cost and sustainability metrics, and like, does the total benefit outweigh the cost? Like, I think, I'm not an economics person by any means, but I think in like the far distant future, I think that would be like an interesting kind of collaboration area for me, is like, if we are doing all these interventions for building, like, is that actually better than some, some other possible interventions?
Yeah, and it's gonna be one of those rambling questions, where I'm not sure what the question is, but so like, I'd like, with full respect to the work, it feels like the spaces from where you're working and your dreams of implementation have a pretty large like distance in terms of things that need to be grown. Like when we're going from one scale to the next, I'm like, there's a lot of, you're entering the like desert of like, not desert, but the like open space of possibilities.
Yeah,
which is
sure.
kind of intense. And I'm wondering, as far as like, what you feel like is kind of the branch between, or what you feel like the tangible things are that might come up out of a research institute like this, right? Is to say like, all right, well, before we can get to taking something at this scale and putting it on an entire building surface or like an urban environment, like, what do you feel like are the sort of tangible, and I think the installation in the center is a really good example, but other places where you maybe envision that as something that was maybe built inside of the community of people making and creating here at Alice?
Yeah, I totally agree with you, and it's a great question. And I'm really thinking along these lines of like this kind of intermediate scale, like that they're, let's go back one slide. I think we can do, so my idea is like, we can start at the centimeter scale on a lot of these things and understand, that way we're not just like building a bunch of big things and tearing them down. Understand something at this scale. And then I do think it's going to be an iterative, like kind of construction process where we're just building these things up and seeing what works and trying to use theory and simulations whenever we can. So we're not so wasteful, but I'm really targeting this kind of intermediate scale as a demonstrator of like, you can go a bit bigger than this. And I think these would be appropriate for demonstrators in an indoor exhibition space, but also like outdoor on campus. If it's like a wall with kind of hydroactive panels, this can be outside and we can actually see what happens like in the real environment, and there might be wind loads and things like that. So yeah, for me, I think a lot of this intermediate, like I use experiments primarily, but also simulations and theory. And I think all three ingredients are important, but I think especially on this kind of upscaling part of things, then I think experiments are really important for me.
Yeah, no, I mean, I see things like this as like a really interesting potential place where students become a part, like, we have a lot of students in this place that are really interested in actual like physical tangible.
Yeah,
builds and
absolutely.
Things like that. So it's an interesting branch to sort of think about.
I definitely agree. I think a lot of, in my experience, a lot of students are really interested in, and I think it's, you know, depending on the project, could be appropriate for students ranging from undergrads through PhD and postdocs who, yeah, are interested in, this is my project, I'm gonna build a big thing and it's gonna work. We'll see how it goes.
I'm wondering if there might be like the other side of the coin with Danny's question, like the tangible intermediate scale. Do you think that with the experiments that you've done, the math behind it all, there's enough fidelity to potentially do like virtual simulations of these materials?
Yeah, for sure. And I think it's gonna be really valuable for like, before we build something big, like simulated or use, I don't know, form finding or something like that for stability questions, especially. I certainly think there's a place for that. Yeah.
Sort of thinking irresponsibly, but all you really need is an example like Crystal, like large scale environmental thing and get a lot of press for it, and all of a sudden, like, how do you get from all these questions, how do you get from good concept, but how do you deploy in reality? How do you attract the people who have the resources to make this happen in real life? Then I thought like Crystal, but yeah.
Yeah, I mean, this like outreach idea is not only outreach to, you know, young students, but also the community, and I think, yeah.
Yeah, I mean, would you
maybe.
be disappointed if in 10 years these ideas don't get built into the real physical environment, or would you be like, cool, I did my science, I'm happy?
That's a tough question. The real physical environment, I think yeah, my imagination for the next 10 years is kind of up to this, like, let's demonstrate it. If some architect is like, oh, we actually need this and we really want to, like, I would love to work with them and get it into the real environment, but that feels like a big bonus for me, to be honest.
Last chance for questions. Chris, you're still online, anything? Or you have a question?
I'm just wondering if there are any other examples of like living materials or biomimicry in architecture, maybe in cities specifically that inspire you or that you're interested in?
Yeah, I think really you said biomaterials. I think that's something I'm so interested in because like they're active and alive and you know, I think there's a big place for engineered materials, but also like this intersection of like composites and stuff, I think would be so cool because it's kind of more sustainable probably. And so that's inspiring to me there. Yeah, you know, I showed those green roofs and walls. So things like that, I think like bio inspiration is clearly coming into all of these types of designs. Yeah, I think honestly, like the examples I showed are inspiring to me in a lot of ways. And yeah, otherwise I would probably turn to biology and nature.